We are into manufacturing of welding equipments and induction heaters and automation solutions at SigmaWeld. And we have presence across all industries and pan-India. We have exports to a couple of countries as well. So without taking much more time, I would like to now pass over back to Dr. Krishnan.
Nimesh. Yeah. So warm welcome to all of you, those who are present in the WeldTech talk today. So today we have Dr. V. Ananthnarayanan, who is well known as Dr. Anthony in US. So he is a PhD and MS in PhD from Ohio University, US. And he is a BTech in Metallurgy from the Indian Institute of Technology, Madras. And he is a founder and president of Innovative Welding Solutions. Its factory or it's in fact a laboratory specializing in the welding and lightweight material. So he has provided effective solutions to chronic welding to more than 100 factories in several countries in North and South America, Europe and Asia, with hands-on problem solving on a variety of structures, components and materials. So he is also an expert in resistance spot welding, and he has been a welding technology consultant to US Air Force since 2016. And he has got a lot of US patents to his name and also a lot of international patents. And he is a distinguished alumnus of the Ohio State University in 2005 and also has received many awards in past, including President's Award for Intellectual Property Excellence and induction into the Innovation Hall of Fame, Delphi Corporation in 2006. And he is author of 35 US patents on welding and as I already told, and another several international patents. So it is really our pleasure to have Dr. Anthony with us today. Sir, over to you for the session.
Thank you, Dr. Krishnan, for the introduction. As he mentioned, I operate an ultra high current welding research laboratory in a suburb of Detroit, Michigan, and work mainly on welding beyond the handbooks. That's what interests research scientists, and also do problem solving for large volume industries. So those are two things we have been doing.
Yeah.
And we thank you all for taking the time to listen to me today on some of our thoughts on the welding of aluminum.
Yeah, I think there are more than 120 participants as of now.
Okay. Yeah. Can you all see my screen clearly?
No, not yet.
Not yet. Okay, so I have to share my. How do I have to share my screen then? Okay, share screen.
Nimesh, the rights are already given? Yeah.
Yeah, I think Sachin is the.
Yeah, it is visible now. Yeah, it's visible now.
You can see my screen now?
Yeah. Yeah, you can make it full screen and go ahead.
Yeah, okay.
Yeah, good to go.
Yeah, the topic of today's talk will be practical challenges in the welding of aluminum. And the contents will be a basic discussion of aluminum alloy basics and weldability issues. When you weld aluminum alloys, you have issues with hot cracking, liquation cracking, loss of strength, a good amount of distortion of the welded structures, sensitization, corrosion, and several other issues which have kept this inexpensive and lightweight material from being used effectively. So I'll be briefly describing these problems and some potential solutions to them as well. Then I'll talk in a fair amount of detail on arc welding of aluminum alloys, equipment considerations, process details, and operator techniques, and mention briefly about resistance spot welding of aluminum alloys, issues in doing that. And then briefly mention some innovative aluminum alloy welding solutions from my own laboratory. And if there's a way forward where any of the participants would like to work on some of the issues that we come up with during the talk, I'll be happy to answer questions or ask facilitate any work by them as requested. So coming to aluminum alloy basics. Aluminum alloys are grouped under 8 different alloy groups. And usually they are designated by a 4-digit alloy group number. Alloy groups with 1XXX are unalloyed aluminum with greater than 99% purity. And 2000 series alloys have copper as the main alloying element, and they are heat treatable to high strengths. And the 2000 series alloys are mainly used by the aerospace industry. And 3000 series alloys have manganese as the main alloying element. 4000 series alloys are used mainly as filler material and have a fair amount of silicon in them that makes them low melting. And 5000 series alloys have magnesium as the main alloying element. They're used extensively in the manufacture of aluminum boats and ships that go into the sea, since the alloys have good marine corrosion resistance except at the weld areas. And 6000 series alloys are used very commonly in automotive body panels. And magnesium and silicon are the main alloying elements. The 7000 series, the main alloying elements is zinc. And again, it's used mainly by the aerospace industry. 8000 series are special alloys, such as aluminum wires for electric cables and so on. So what differentiates these alloys are, firstly, whether they are heat treatable to high strengths or not. And you can see here that 2000, 6000, and 7000 series alloys are the ones that are heat treatable. And the 2000 and 7000 series alloys are not considered very weldable. So they're used mainly by the aerospace industry. If you have seen, we all have seen aircraft body panels being riveted and not welded because of the weldability issues with these 2000 and 7000 series aluminum alloys. The 6000 series are heat treatable to high strength and are used in body panels for many vehicles, such as the Ford F-150 here in Detroit. And what differentiates them, as you see on the right side here, is the melting range of the alloy. If you see the alloys 6061 and 5456, the range of temperatures between the solidus and the liquidus, as shown in this slide, is roughly around 70 degrees Celsius. And if you look at the two alloys below, the 2000 series and 7000 series alloys, the melting ranges are more than 100 degrees Celsius, more like 130 in the case of 2024, and almost 160 degrees Celsius in the case of 7075. And the difference between the solidus and the liquidus is called the coherence range. And higher the coherence range, the higher the tendency for hot cracking of a weld metal as it solidifies. And That's one of the main reasons why these two alloys are not considered weldable. If you look at efforts to spot weld these alloys using conventional methods that are used in the manufacture of, say, the Ford F-150 aluminum body, you can see that the alloy 5000 series and 6000 series alloys give you very good buttons in a peel test of spot welded aluminum, whereas 7075 gives you some questionable buttons, and the brakes are mainly in the sheet metal. And with a 2024 alloy sheet, you cannot even get a good peel test done. The separation is entirely along the interfacial interface of the weld. Yeah. So this shows the effect of the coherence range on the weldability of these alloys and why folks don't like to spot weld the 7000 and 2000 series alloys. And another problem with aluminum alloys is the liquation cracking, which is the partial melting of a second phase in the heat affected zone of the alloy. And it's not tramp elements in the material that makes this cracking happen, but alloying elements such as copper, silicon, and magnesium that are added in the alloy. And I will show you some micrographs later that show second phases of this alloy in the heat affected zone that melt during welding and cause this liquation cracking. Phases such as Mg2Si and Al6Cu Mg4 and other phases are the sources of such liquation cracking. And what I show here is a micrograph of a resistance spot weld of a 5000 series alloy, where these magnesium-rich second phases have cracked due to the welding heat. They have actually melted and cracked during the welding and post-weld cooling operations. So this kind of a crack obviously makes the structure not suitable for service, and it's a problem when you weld these alloys which have second phases that can cause such heat affected zone liquation cracking. And some of the potential solutions for this liquation cracking is to, if you are doing arc welding, you can use filler metal containing 5% or more magnesium that lowers the melting temperature of the filler metal and allows it to provide a feeder for already solidified regions, so they solidify without cracking. And also fillers with grain refiners such as zirconium can help as well. And edge preparation and root gap can also be done in such a way that sufficient filler metal feeding is enabled during the cooling of the weld post-welding. So these are some of the techniques that folks use while trying to address this liquation cracking issue, but none of these work very well if you are spot welding this alloy, or if you're trying to resistance seam weld this alloy using conventional methods. The aluminum alloys also are subject to sensitization corrosion, particularly the 5000 series alloys, which happens due to the precipitation of magnesium aluminides in the heat affected zone parallel to the weld edge. There is a temperature range in the heat affected zone that is favorable for the formation of these magnesium aluminides parallel to the weld edge in the heat affected zone. This is very similar to the intergranular corrosion of stainless steels that some of you may be familiar with, where the heat affected zone of a stainless steel, if it has higher carbon contents, or if the heat input's very large, tends to become susceptible to corrosion in the heat affected zone. So this is somewhat similar, and folks use low heat input and cooling of the heat affected zone. But this is a serious problem in the welding of aluminum boats and ships that go into the sea. I have known some aluminum ships that go into the sea, come back to the dock every 2 or 3 years, just to gouge out these sensitization corroded lengths parallel to the weld, and then deposit new weld metal and go back to the sea. And during that time, the ship or the boat is not available for service. So this is a serious problem that if the welding industry addresses, it would be a useful contribution to the manufacturing industry. Another problem with the formation of magnesium aluminides is that the adjacent regions lose magnesium that goes into the formation of these aluminides. And as you know, much of the strengthening of the 5000 series alloys is due to the solid solution strengthening by magnesium atoms. So when magnesium atoms are lost in the heat affected zone in the formation of magnesium aluminides, it's a double whammy. The area becomes sensitive to saltwater corrosion and it loses strength as well. And other issues with aluminum alloy weldability are 50 to 70% loss of strength in the weld and heat affected zone areas. And if you weld a 6000 series alloy like 6061 T6, a 50 to 70% loss of strength in the heat affected zone is not uncommon. And this is why the aluminum alloy structures have not gained widespread use in structural applications that involve cyclic loading and other heavy stressed mechanical loading applications. And the loss of strength occurs even in non-heat treatable 5000 series alloys, as I mentioned. So the recovery, recrystallization, and grain growth rob strengthening effects from cold work as well. And what can one do here? One can tack weld more to help with the distortions and assemble compressive stress if possible, so that the residual stresses are not so adversely affecting the application, and only make welds that are as big as needed, no bigger. If there's a thought process that larger welds can hold more load, that is a completely wrong idea with respect to aluminum. Now I'll talk a little bit about the arc welding of aluminum alloys and mention at the end of this talk some of the things we did while welding a door panel for an automotive application, the door panel made of aluminum. And initially, I'll just introduce some of the techniques used in the arc welding of aluminum. All arc welders for aluminum need push-pull feeders because the alloy wires are soft. You cannot just push the wire into the weld gun conduit like you push a steel wire. You need a push-pull feeder, and the feeders are very close to the contact tip in these guns. And the conduits are also made of Teflon. So it's very necessary to keep the conduits in a smooth circle and not step on them, and handle these welding conduits and welding setups very gently when you're welding aluminum. Secondly, the welding current waveforms and polarities play a significant role in both gas metal arc welding and gas tungsten arc welding of aluminum. And as you all know, aluminum has a very high affinity for oxygen. If you, for instance, do some use some emery paper and clean the weld area free of oxides. And then you take a break and go to lunch and come back. The oxide has already formed on the surface you just cleaned prior to the lunch break. So that's how oxidizable this metal is. And it needs cleaning for effective arc starts. And it also needs cleaning when you have multiple welds, like in a door panel, where you start and stop, where a robot starts and stops a weld and then skips a certain length and goes to the next weld to be done and makes the weld and so on. There, the main problem is the heat from the first weld tends to oxidize the start of the second weld. The second weld doesn't start as well as the first weld, just because the first weld itself oxidized the area that you're trying to weld in the second weld. So there are some techniques that I would discuss at the end on how do you deal with that. And the oxidation of the surface of the aluminum is a very important aspect of arc welding aluminum that folks need to understand well. The oxide is not only a barrier to good arc starts, but is also a problem creator from the point of view of excessive porosity in the weld metal. The oxide has a very high solubility, very high affinity for absorbing water. And if it's a rainy area in a city like Mumbai and you have aluminum oxide on the surface, you can bet that the weld would have quite a bit of porosity. And how do you deal with these are some of the issues that are discussed here. And the negative polarity used, say, when you're doing alternative current waveforms in welding aluminum, helps the cleaning of the surface of parts. Because when the polarity is negative, it's the electrons that hit the metal, and they tend to clean up the surface prior to the welding. And also the negative polarity makes the positive ions hit your electrode wire, so you get very high deposition rates as well. So to understand the effects of these waveforms in aluminum alloy welding is very important. And if you look at TIG welding, you can have balanced AC sine wave technologies at 60 hertz here, or in India, it may be 50 hertz. And the positive half cycle is cleaning, the negative half cycle is penetration. And so if you have AC square wave technology, you can have more cleaning or more penetration as your joint geometry dictates. And some of the arc welding waveforms are shown here. I'm not trying to recommend one manufacturer of weld equipment versus another. Many manufacturers like Lincoln and Hobart and others also have their own special waveforms for welding aluminum. What they commonly do is to superimpose low frequency and high frequency pulses. Current pulses are shown here. You can see here that there are, these are not low frequency and low amplitude and high amplitude. I have an error here in the slide that I will correct before sharing it. High current amplitude and low current amplitude pulses, and the penetration and wetting during the high current pulses and solidification during low current pulses. Why do we need this? One of the reasons is that aluminum is a very conducting metal. And if you keep welding at a current that melts the initial start of the weld, by the time you travel a certain distance, the weld and the metal get too hot. And there is a need to cycle low and high currents like this to maintain a constant weld current width. And you can adjust the duration of these in depending on your part material thickness combination and joint geometry to get an acceptable weld bead that has uniform wetting and penetration along the length. And this kind of imposition of low current and high current pulses is also done in the AC mode. It permits high deposition rates and is designed to weld thin metal with or without large joint gaps. Again, my apologies for this error here. It's not low frequency, it is low amplitude or low current. Many gas metal arc welding power supplies for aluminum permit changing weld schedules and weld current along the length as well. Filler metal selection depends on the grades welded and mainly intended to provide low freezing range filler that melts at low temperatures, such as silicon-rich fillers, which are 4000 series alloys. And the melting range of the filler should be close to the solidus of the alloy welded. And while welding aluminum, it is always necessary to do a push angle technique. A pull angle technique does not work with aluminum because of the oxide issue that I talked about. There is a need for the plasma to clean the metal ahead of the arc as you proceed. So a push angle is always essential, whether you do gas tungsten arc welding or gas metal arc welding, and use higher welding speeds and lower heat inputs wherever possible. And faster cooling rates from higher speeds help counteract hot cracking tendencies as well. And I show the push angle here that is commonly done with MIG welding or TIG welding of aluminum. And shielding gases for welding aluminum are either pure argon or argon-helium mixtures. The addition of helium causes the arc voltage to rise, the arc to become hotter, and the weld bead to become a little bit wider. And the heat flow is in aluminum is very different from that in steel. One of the techniques I have seen folks do, such as those who weld aluminum gasoline tankers in Tennessee, are they do the welding manually. They don't do it using a robot. And as they are traveling along the weld length, they maintain the same push angle and the same travel speed with their hands, but their hands are going up and down as they go along the weld. When they go down, they get penetration, and when they come up, they get cleaning and good fusion, good wetting. And then they keep doing this with a good cycle, and they're all trained and certified to provide good fusion and penetration. And they are checked frequently by sectioning checks and also by bend testing, as you know. And some of the boat manufacturers and other ship manufacturers use water-cooled fixtures to cool the heat-affected zone areas, so they don't become susceptible to the sensitization corrosion that I talked about. So this may make some of the difficult to weld alloys, particularly for marine applications, more weldable. So when you are designing fixtures, please think about this aspect. And lap joints are more often used with welding aluminum alloys to provide ease of fit up and edge preparation. And pre-weld cleaning of aluminum alloys is essential to avoid porosity in the weld. As I mentioned, it's not a good idea to store aluminum alloy parts to be welded in open atmosphere close to a rainy area, for instance. And the oxide layer, as I mentioned, has much affinity for moisture. And the gasoline tanker welders in Tennessee that I mentioned always get their sheets to be welded with protective covering, somewhat sticky covering that doesn't leave any residue on the metal when they are removed. And they are removed just prior to welding, and then they weld it, and then they remove another covering about a couple of feet from the weld, so the covering doesn't get hot. And it's essential to also send the shielding gas for aluminum arc welding through a drying bulb to avoid porosity. If you have water content in your shielding gas, you are sure to get quite a bit of porosity in the weld. This was one of the problems I helped solve using the simple use of a drying bulb when they were trying to weld aluminum landing strips for aircraft for use in the Iraqi desert a couple of decades ago. And it's necessary to store the parts to be welded in dry indoor areas, especially when it's raining. I'm kind of repeating this since I know Mumbai has quite a few of these rainy areas. Weaving techniques also need to consider thermal conductivity of the alloys. The nozzle is rotated to do the weaving sometimes. And one of the problems with welding aluminum is the weld tends to bubble up. The bubbles are mostly due to hydrogen that's dissolved in molten aluminum. And oils in the weld interface are parts to be welded stored in a moist atmosphere. Our oxide layer in the cut surface are causes of these moisture contents and also the shielding gas. And cleaning these up usually helps with them, and weld as soon as possible after cleaning, and keep brushes dry and oil-free, and keep welding gun nozzles clean, and reduce the stick out. The stick out in aluminum welding does not change weld bead profiles as severely as stick outs in steel welding. Because when the stick out in steel or stainless steel welding changes, the heat generated along the wire after it exits the contact tip changes significantly. With aluminum, that heat generation change is not very high, but still it's a good idea to have low stick out so you don't get moisture infringement from outside, and also the shielding gas coverage is good. And if your MIG welds with aluminum end up bouncing the wire without an arc strike, try cutting the wire trip and cleaning the start of the area. And this was found to be very necessary when we were welding door panels of aluminum door panels for in an automotive application. We didn't have to cut the wire tip there. The aluminum arc welding power supplies have a way of finishing the previous weld while leaving the tip of the wire very sharp. So in all cases, use that feature, and when you finish one segment of a weld, make sure that the wire sharpening feature in the arc weld power supply is used effectively and the wire tip is sharp for the next start. And also make sure that you don't have too many starts and stops while welding any sheet metal structure. If possible, make welds continuous, or if possible, adjust the welds so that the heat from one weld doesn't oxidize the start for the other weld. And also use a high run-in wire speed for initially at the weld so that you get good weld starts before the regular wire feed speed kicks in. And when you're doing TIG welding of aluminum, High frequency arc starts help clean up the aluminum surface locally and help strike the arc well. And with MIG welding, high frequency alternating current starts are not possible to superimpose on the waveform. And you can use a crater fill time of around a second with reduced current. This will help fill the weld crater so it doesn't crack. And the gun should not be withdrawn as soon as the trigger is released. And a burn back time of about 10 seconds max will help make sure that the wire tip ends in a sharp configuration and make sure that it doesn't stick to the contact tip upon the finishing of the burn back time. When you do gas tungsten arc welding, the operator has hand control of the welding current, and you need to reduce the current as you reach the end of the plates being welded as they are hotter. And if the welding is automated, the welding current needs to be reduced with travel distance. And at the end of the weld, lower the current and feed more filler wire to make a good crater as well. And sufficient pre-gas flow and post-gas flow should both be optimized. And I've talked about the weld bubbling up already. I will talk about some solutions for some of these problems which were developed in my laboratory, which actually involved focusing weld current at the intended weld nugget region. And such focusing methods also permitted cooling of the heat affected zone with water-cooled copper. They use large water-cooled copper alloy electrodes that you would not find being commonly used in resistance welding. They use low melting filler metal between high coherence range materials that we talked about, like the 2000 series and 7000 series alloys, where we didn't even get good buttons in a peel test, as you saw in photographs of peel tested parts earlier. And this kind of a focused melt resistance welding also helps manipulate temperature profiles. This talk is not meant to describe this method in detail. If this method needs to be described in detail, I'm ready to make another presentation of about an hour or so that would show tooling, electrodes, parts welded, and so on. But it's just meant to give a flavor for some of the parts welded and some of the solutions developed by using this methodology. For instance, here we are resistance spot welding 2 aluminum alloy plates. Each plate is 6.25 millimeters thick. And normally one would not even attempt to resistance spot weld these, these plates. And if you see the copper alloy electrodes I'm talking about, you see how large they are and how they cool the heat affected zone during welding. And so these large electrodes have low electrode wear, and they last a few thousand hits between between redressing operations. As you know, if you're spot welding aluminum in an automotive factory, it's hard to have more than 60 or 70 hits between redressing operations for the electrode tips. And a few thousand hits between redressing operations is almost unheard of. So this kind of a focused melt resistance welding permits the spot welding of these kind of thick and thin metals with very high electrode life. And also there is no dust or spatter from the electrode metal interface. And when you cool the heat affected zone, some of the non-weldable aerospace grade alloys become very weldable. As you see here, the alloys 7075 and 2024 T3 have very good buttons, and they had good microstructures as well. Due to a lack of time, I'm not going to show microstructures of these alloys. And what is also important about this focused melt resistance welding is that the diameter of the weld in all these cases is the same, 10 millimeter diameter button. And the thickness of the sheets welded is not the same. The 5000 series alloy has 2.5 millimeter thick sheets welded, and the 6061 alloy has 1.6 millimeter thick sheets welded, and they both have the same button diameter. So the focused melt resistance welding method allows you to select the weld size irrespective of the sheet metal thickness. And that way you can also select the weld strength of a particular spot weld as well. And if you look at micro hardness profiles of these focused melt resistance welds and conventional welds, you can see here the darker bluish black profile is the micro hardness traverse across conventional resistance spot weld. Here is the fusion boundary. And as you come into the heat affected zone from the fusion boundary, the hardness dips very much. If the parent metal hardness was about 110 Vickers, the hardness dips to something like 50 Vickers. That is more than 50% loss in hardness and strength in the heat affected zone. That makes these alloys not so serviceable in cyclic loading. And with the focused melt resistance welding, the hardness increases as you come out of the fusion boundary, as the area has not been softened very much. And the heat affected zone micro hardnesses are closer to 85, 90 Vickers, and only about these welds are about 50% harder in the near heat affected zone, and also have similar increase in shear strengths. And the focused melt resistance welding permits the welding of thick-thin combinations not permitted by aluminum welding handbooks. If you look at the Resistance Welding Manufacturers Alliance of the AWS, American Welding Society, they recommend not spot welding aluminum parts with a thickness ratio greater than 1:3. And these are 1:10, welded very well. For a military application in the United States. And the common thought process with aluminum welded structures is also that they are not good for fatigue loading or cyclic loading. And that paradigm is also broken up by this focused melt resistance welding technique. You can see that the 6.25 millimeter thick sheets that I showed in an earlier slide have been welded very cosmetically. If you move your finger across this weld, you will not feel the weld nugget at all. You can see how smooth the outer surfaces are here. And you can also see the grip marks here on the sides of the sheet metal. And these grip marks were made when these welds were fatigue tested to a specification specified by a flatbed truck manufacturer in Canada. And these were loaded from 0 to 1,700 pounds. My apology for the American units here. That's about 0 to, I would say, a 600 kilogram load at 1 cycle per second for 30,000 cycles. And the welds don't even look like they are tested. And these welds pass the fatigue test very comfortably. So with this method of welding, it is definitely possible to weld thick-thin aluminum metals, heat-treated aluminum alloys with high structural strength for fatigue loading. And when you cool the heat-affected zone using water-cooled copper alloy electrodes, you see that the second phases in the heat-affected zone do not melt and crack anymore because they are kept cooler by the water-cooled copper alloy electrode. The separation between the weld interface here is due to peel testing, The lower side was pulled apart in an effort to do a peel test. And in the peel test, obviously, in this case, the materials did not come apart. And you can see that cooling of the heat affected zone helps you counter liquation cracking as well. And these are some electric vehicle aluminum cable welds being commercialized. These were recently looked at by a major Japanese company called Yazaki, and to whom I had sent these welded cables for consideration for use in their electric vehicle construction. And you can see here that the focused melt resistance welding has actually melted the aluminum wires into a solid. If you look at this area of the weld, and it's contained on all four sides by silver-plated copper welded to a brass connector. Now, why did I weld this combination? It was welded because one of my American customers wanted this, and the Japanese have actually asked me to weld aluminum connectors to these same aluminum cables, and those are nearly ready for shipping to Japan for testing. And the point I'm making here is that these cables would be very useful for a potential large volume industry like the electric vehicles, which are presently using only copper cables, which are both heavier by a factor of 3 or so, and which are more expensive by a factor of 10 or so, in connecting the electric vehicle motor to the battery and the inverter to the battery and so on. Potential savings of, say, a school bus construction in just the cable material costs would exceed $1,000. And these savings are not being realized only because the welding of these cables to these connectors has not been possible effectively so far. And I believe that paradigm has changed, and hopefully this will see commercial implementation sometime soon. And I'm not sure whether I delivered the intended talk to all of you, but I have tried to talk about aluminum alloy basics and issues with weldability with respect to coherent ranges, hot cracking, liquation cracking, some distortions, loss of strength, were all presented with some potential solutions. And arc welding techniques and equipment considerations were discussed in detail. And some work from my laboratory, which I believe are innovative, were presented with examples. They helped counteract some of these issues, like liquation cracking and applicability to cyclic loading particularly. And I believe that the present engineering and industry approach to the welding and use of aluminum structures is badly outdated. They have not exploited the potential of cooling heat-affected zones with water-cooled copper nearly enough. And they're all married to old, outdated teachings and handbooks and methodologies and design manuals, and are refusing to come out of those. And there is a need for this aluminum industry to wake up and smell the coffee. And codes and standards, not only in this country, but in Europe and Asia, are badly outdated, including in Japan. And this is keeping a very inexpensive, lightweight metal from being used to its effective potential. So I think there's much to be gained by using lighter and less expensive aluminum. We need working groups that increase awareness and want to work beyond the handbooks and want to prove that the handbooks are not there forever, but are meant to be updated as we learn from our experiences. And if you all want to form any such groups, any such lightweighting efforts, I will be happy to work with all of you. So with that, I conclude my talk and I'm open for any questions.
Yeah, Dr. Anthony, there are a few questions in the Q&A.
Mhm.
If you can go there.
Okay. Okay.
You are able
Okay.
to see? Yeah.
Okay. I Sendamai Selvan. Let me know your YouTube channel name. Sorry, I don't have
No,
one.
leave that apart. That we will
And,
share with them. Yeah.
additive manufacturing is performed in aluminum. Yes, additive manufacturing is performed in all kinds of alloys, and there are many working groups on them. I don't have much experience with that. I haven't been a part of these additive manufacturing groups. I have a basic difference of opinion with them. That's why I haven't participated in these groups. My difference of opinion is that when you melt dissimilar materials together, whether it's in a small volume or a microscopic volume or a large volume, the metallurgical effects are the same. And by doing additive manufacturing of a variety of materials without controlling the metallurgy, it doesn't appeal to me very much as a metallurgist. And also, I have participated in some American Society of Mechanical Engineers boiler and pressure vessel code meetings. When inspection of these additively manufactured components is to be done, the people presenting the additive manufacturing court cases on how they should be inspected are not willing to include tests like liquid penetrant testing, which would pick up micro cracks and small defects in these parts. So I think this has a large amount of funding and a great amount of work is being done with many working groups, but it has not appealed to me to join, so I don't have much experience in it. I'm sure additive manufacturing is performed in aluminum as well. And then I go to the question from Kiran Patel. We are a manufacturer of aluminum column in Vadodara, India. We have good welding and radiography result in 5083 materials with manual GTAW and machine GTAW, but we have a major issue of porosity with 6061 pipe butt welding where we use. I will be happy to work with you, Kiran. I can volunteer that. I don't need to charge you for any services. You see at the bottom of my slide, you see my email address. If you work with me there and give me some photographs, procedures, I can work with you to limit or eliminate the porosity.
So we will pass over your mail ID to Kiran.
Yeah, sure.
Yeah.
Kiran. And then Pradeep Subedar, aluminum shows a lot of porosity and RT film. Is there any volumetric NDE to be used for aluminum welding applications? I would not do volumetric NDE. I would eliminate the porosity. Again, if you show me some of your techniques and some of your weld areas, I can counsel you on how to get rid of this porosity, as we did with the aluminum landing strips for the US Air Force in the Iraqi desert. So the porosity issue is real. I know many of you are facing it. One common technique that can be used is to make sure that your shielding gas is sent through a water absorbing bulb, like which contains, say, something like calcium chloride. So the shielding gas comes out of that bulb without any moisture as it enters the welding gun. Number one. Number two, store all your parts in areas away from doors and wet areas. Number 3, clean them and weld them clean them just prior to welding and weld them immediately. Don't clean them and leave them for a while before you do the welding. These are common techniques you can use. There are also techniques of your electrode angles and other fit-ups and root shielding gas coverage and so on. I can counsel you on those if you provide me with some details. And then, okay, I think I answered this one already. Any development on aluminum 5082 to SS304 welding? I am a specialist in dissimilar material welding. What have I welded this in this regard? Some very difficult combinations, such as I had a NASA project where I welded rocket nozzles for them, and I welded a titanium tube to a stainless steel tube. Prior to my work, NASA was only able to braze this combination. The titanium alloy was not metallurgically weldable to a stainless steel alloy. And I was able to develop a tube-to-tube welding procedure where the alloys were effectively welded together, not brazed. I also do spot welding of aluminum sheets to steel sheets without any filler metal, without any plating. And if someone's interested in that, I could work with them on that. And on this question, whether I can weld aluminum 5082 to stainless steel 304, I need joint geometries, thicknesses, and intended use. What are the expected weld metal properties? Again, I can work with you preliminarily on emails. If you send them to me, I can counsel you on those. And if some samples are needed, my laboratory can weld all kinds of dissimilar material combinations. If there's an interest here, I could show photographs of the weld machines in my laboratory. And is it a good idea to join aluminum alloy 5052 using hybrid TIG-MIG welding? What could be the possible problems? Again, you have to show me some joint geometries before I can counsel you specifically. I will be willing to work with you if you give me some more details. I have talked about sensitization corrosion problems in arc welding, the 5000 series alloys. That would be a problem whether you do TIG or MIG or hybrid TIG-MIG. If you gave me more details on why you're using a hybrid process instead of one or the other, and what are your joint geometries and requirements, I could probably counsel you on that. And if we weld a 304 stainless pipe of standard schedules with 316 stainless, after welding near HAZ area, different colors appears. What was the reason? The colors are mainly due to oxides of alloying elements. So long as your weld metal properties are good, and so long as your stainless steels are not sensitization, corrosion sensitive due to the welding, you may be all right. What you need to do is to take a look at a cross section of your weld and see if the color is only on the surface, in which case it's probably not a problem. Or does it affect the weld quality deeper? If you need to counsel a little bit more, I can be open. If you send me some photographs or send me some emails, I'll be happy to chat with you. And the anonymous attendee, cooling HAZ during welding is the reason behind the good weld in focused melt resistance welding. Yes, absolutely. And also the ability to focus weld current at the area where melting is needed. and heat only that area. These are the two big strengths of the focused melt resistance welding: cooling of the HAZ and the ability to focus the current into the area you want while maintaining a very low current density on the electrode to metal interface. So that interface remains stable in large volume manufacturing. So those are the strengths. Does solidus and liquidus line have a major effect of welding steel and its alloys? I have not heard of this being an issue with steels and their alloys because Dr. Krishnan, do you want to address this maybe?
Yeah, I think it will have some role in case of, like low alloy steels. Yeah, because that will decide your transformation part. But not sure whether it is specific to aluminum.
Yeah, the solid and liquidus line, the coherent range, whenever you weld any long freezing range alloy, which means you have a large difference between the solidus and liquid temperatures, your weld metal cools with a pasty solidification. What you would use in these cases is a low melting filler, which melts close to the solidus temperature of the alloy. So you get continuous feeding into the weld areas that are solidifying, so you don't crack very much. So I have not heard of this being a major problem with the welding of steel.
Yeah.
Very informative talk. Thank you very much. Can 5-6 series be welded with DC GMA? Yeah, definitely they can be. But as I said, it may be good to do the high current and low current pulsing, as I showed in some of the earlier slides. What's your opinion on pulse GMAW or GTAW? I think they are very useful in controlling the progress of heat along the weld path. And it's very easy to use these pulsed GTAW, pulse GMAW methods to control the heat along a long weld so that you get uniform bead characteristics. With GTAW, if you're doing that, it would need a good amount of optimization and changing currents as you go along. This is one of the reasons why the gasoline tanker manufacturers in places like Tennessee here do all their GTAW with manual expert welders. They can see the bead widening and just speed up their travel speed, or they have hand control on the welding current that they can lower. And with GMAW, it may be a lot more easy to optimize heat distribution along the length of a long weld. If you're using low current and high current pulses alternately. How to prevent hydrogen porosity during welding in aluminum? I talked about this already. Make sure that your shielding gas goes through a drying bulb that contains water-absorbing chemicals like calcium chloride. Make sure you clean the oxide layer of the weld area just prior to welding, and don't store your electrode materials or your parts in wet areas. And make sure that your welding area is dry and free from moisture. And how to make calibration to welding machine. Okay.
I think it is not specific to, it's a very generic. Yeah, I think we can skip that. Yeah.
Skip that. I'm not sure what you mean by calibration.
So I think it is calibration of the welding machine, before you use it for a given application.
Okay.
So you calibrate it to see that it gives the right output.
Right output. Okay. Yeah, we are interested in friction stir welding of long seams for manufacturing white panels. Can you support us? I don't have much experience in friction stir welding, but I can counsel you. I have not needed experience with the welding process to understand issues involved, since I have worked on a variety of welding processes ranging from electron beam welding to laser welding to friction. I have done friction welding quite a bit. I've not done friction stir welding much, but I can counsel you if you want. Alternatively, one of the activities in my laboratory, if you will permit me, can I show another slide on this one, Dr. Sivaraman, Dr. Krishnan?
Yeah, we can have. I think maybe we keep it for the last.
Last, okay.
Yeah.
I am developing at this time for the US Navy
Okay.
mash seam welding of aluminum alloys. The 5000 series alloy that I mentioned becomes corrosion sensitive in the heat affected zone due to welding heat. I am developing welding for it using a mash seam welding process where I flood the weld area with water coolant during welding, so that the sensitization doesn't occur. And then the sensitization corrosion of the welded structure would not be an issue for the US Navy.
Okay.
I'm developing some of these. I could send you some samples, or I could. I would recommend some conventionally seam welded aluminum, like what I mentioned, in preference to friction stir welding, because the friction stir welding can be done very well, very effectively. It takes a great deal of expertise to optimize the tool geometry and to maintain the tool geometry during your manufacturing operations. Even I've seen experts having trouble optimizing them and maintaining them. So this may be a somewhat difficult exercise for you. I can counsel you, but I'm not sure how much I can help with friction stir welding. I would recommend an alternative process like the mash seam welding process. I can send you samples. If you're interested, I could build welding machines that can do that for you. I can show you at the end my mash seam welding setup if you have time.
Yeah.
We are facing big problems with black color layer formation after welding a 6000 series alloy. Cleaning the material with acetone is also not helpful. The filler is 5000 series alloy. If we use 4000 series alloy, the black soot formation will be reduced. Honestly, I'm not sure of the answer to this question. I can work with you on it again if you send me some details to the email address below. Is CMT advisable for 5000 series aluminum alloy plate butt weld, a replacement for multipass? Dr. Krishnan, can you expand CMT for me, please?
Yeah, it is cold metal transfer. It's actually a short circuit GMAW. It's a patented process by Fronius.
Fronius. I'm sorry, I'm not aware of this process very much.
Yeah, I will get him connected with the Fronius people.
Yeah, okay, sure. Whether the application of electron beam welding explored for the welding of aluminum and aluminum alloys. I've not heard much electron beam welding being done. I've not seen much electron beam welding being done anywhere anymore. A lot of people are moving to laser welding instead, which can do most of the things that electron beam welding can do as well. The laser welding of aluminum has been very difficult issue due to the reflectivity of the aluminum alloy metal for lasers. They've had to use lower and lower wavelength lasers like the blue lasers and the green lasers to weld aluminum. And then the eye protection for any personnel in the welding area becomes a serious issue. If a small amount of this low wavelength blue or green laser escapes the welding chamber and hits the eyes of a person, even if he's wearing safety glasses, colored glasses, it can ruin his or her vision. So there is a need to certify the welding chamber closure effectiveness for these kinds of aluminum alloy laser welds. I don't have much experience electron beam welding aluminum and aluminum alloys. I have electron beam welded stainless steels and zirconium alloys in my work life, but not aluminum. How many times can we repair to weld joints? Oh, wow. I think you are talking about aluminum. Aluminum loses most of its strength even after one welding effort. As I showed you, I can lose more than half the strength or the hardness in the heat affected zone. If you keep welding it to do repair welding, you probably don't have much mechanical strength left. And you're also probably metallurgically affecting it. Any effect of cold work or any effect of heat treatment that you've had on the alloy would be lost. So if you're doing aluminum welding for structural applications, I would recommend that you keep repair welding to a bare minimum. And if you do need to do them, just cut the parts off and then repair weld again. Hopefully you have enough length or enough extra material to accommodate that. Repair welding aluminum too many times is not going to be very good for fitness for purpose. Rajesh Jha, aluminum alloys with scandium. What's sorry, I'm not sure of that. I need to study this. I can look it up and get you an answer back. I'm not familiar. Are you here, Rajesh? What is this application for?
I think maybe he can connect with you,
Yeah, he can connect with me. Yeah. At this time, I'm not familiar with this alloy. How start current and end current percentage affects an aluminum cracking. The start current doesn't affect cracking very much. The start current helps you initiate the arc very much. Typically, you want a high starting current, and a sharp tip, so that and a non-oxidized surface of the metal being welded, so you get a good start. The cracking effect of the current is mainly at the end. And at the end, in order that you don't crack, you want to cool, you want to feed a lot of metal and lower the current. The idea being that you solidify the end of the metal quickly and not very progressively, so it doesn't crack. This is Sandeep, research scholar from the VIT University, Vellore. Recently, we tried joining aluminum and polymer with solid state technologies like friction stir spot welding and friction stir welding. I want to know, is there a criterion to judge whether the joint is qualified or not based on surface appearance of the weld? You're probably doing this joining to, I need a little more details, whether the joint is a structural joint or is it a corrosion prevention joint, or what is the purpose of that? Maybe you can communicate with me on emails and we can discuss this a little bit more.
Yeah, he seems to be a research scholar. I think you can support him.
Yeah, sure. Preheating and interpass heating required for aluminum welding? If yes, and when and why? Actually, I recommend against preheating and interpass heating. Mainly because when you do these, there is a higher tendency to oxidize the joint. And if you're doing short length, multiple welds, like in a door panel for an automotive assembly, oxidized areas are not very good. So I would recommend against preheating and interpass heating for aluminum, actually. During aluminum welding, the strength in the heat affected zone will be reduced. What is the acceptable limit in the PQR? Then if the tensile strength is less than the original material. There are no guidelines on this matter. This would depend very much on the thickness combinations, on the structural application, what you're trying to do, and so on. If you look at the structural welding code for aluminum, when you qualify a welder to do a TIG weld or a MIG weld, you are not asking him to check the strength of the weld. You're asking him to check the cross section, so you know that there is good wetting and good fusion. And you're asking him to do a guided bend test, so you know there is good bend ductility without cracking. So those are the things you can ensure by welding a heat-treatable alloy with any kind of welding, arc welding, spot welding, or even friction stir welding. And you really cannot impose limits on the strength of the material. Whatever you get is whatever you get. If the structure doesn't perform satisfactorily in service, then you need to change the material combinations in it to withstand the structural loading if you want to. Like CO2 shielding gases used with heaters, any possibility of warming argon, helium shielding gases? No, there's no need to warm these. There's a need only to remove the moisture from these gases by sending them through water absorbing bulbs. Professor Manavalan Ilakkuvan, excellent and amazing. Thank you very much, sir. Appreciate your comments. Vijmohan Sharma, you're welcome. Chaitanya Kavade, how start current and end current percentage affects? I think I answered this already.
Answered, yeah.
Can we use normal spot weld machine for aluminum welding sheet? Yes, you can use normal spot weld machine for aluminum sheet thickness of 1 millimeter if you were welding currents that the machine can deliver are at least about 40 to 50,000 amperes. As you know, aluminum spot welding requires higher current, shorter weld times, and higher weld forces. So you're looking for at least about 700-800 kilogram force capability, and you are looking for about a 40 to 50,000 ampere current capability, and you are looking for fast follow through. It is very necessary to follow through fast when you're spot welding aluminum, because when the material melts, it loses strength very quickly, much more quickly than a steel spot weld. And oftentimes, if the electrode doesn't follow through quickly and maintain the weld pressure, there can be an arc flash between the weld electrode and the part welded. So some of the characteristics you need are very high current capability, high force capability, quick follow through capability. Typically for these reasons, an aluminum spot weld machine is quite a bit different from a steel spot weld machine. On the other hand, If you have an aluminum spot weld machine, which is fired by, say, a mid-frequency DC inverter and transformer, you can use that for spot welding steel. That would go down to the weld current needed for the steel very readily. But if you have a normal spot welder that is spot welding steel, you may not have enough current capacity to go weld aluminum. Your slide 26, what's the thickness of the base metal? Let me go up for a second. Yeah, my slide 26, thickness of the base metal was 1.6 millimeters. I suppose coherent range is associated with two metal alloys. No, not really. It is the range of one alloy. It is the difference between the solidus temperature and the liquidus temperature of the same alloy. The liquidus temperature is the one above which the material is completely liquid. The solidus temperature is the one below which the material is completely solid. How many times can we make repair of weld joints? I have answered this already. What's the composition of black soot found often on MIG welds of aluminum? I'm sorry, I have to look this up. I can send some emails on these. Can aluminum alloys and SS be welding using EBW? Stainless steels, yes, I have welded stainless steels using electron beam welding, no problem there. I don't see a problem with in welding aluminum alloys with electron beam as well. It's a matter of how the electrons are being absorbed. It's a very conducting metal, so I don't see a problem in the electrons being absorbed and being grounded. I don't see a metallurgical problem either. So I think the answer is yes. Both of them can be electron beam welded, both aluminum alloys and stainless steels. Is it advisable to cover pass without filler to make good appearance of final aluminum weld layer? I would advise you against adding any heat input to an aluminum structure without the need for it. Oftentimes, appearance is not what matters. The functionality is what matters. If you put in more heat and draw on the bead again, that's commonly not a good solution. You should make a good first-time bead. And if you're doing MIG welding with the pulsing of the welding current with low and high current pulses, as I indicated, you should be able to make a good uniform looking bead the first time around. If you're doing TIG welding also, where the efficiently trained TIG weld operators make very good looking TIG welds the first time around. So if you have the need to make a cover pass, there is a problem with some of your techniques. If you contact me, I can counsel you on that and see if your appearances can be made good the first time around. You don't want to add heat to an aluminum alloy unnecessarily. Mesh seam welding for what? Thank you. I'm developing mesh seam welding for two applications, for automotive body panels. You can weld thin sheets like 1.6 millimeters that I talked about, and weld aluminum body panels together. What the mesh seam welding does, particularly if you flood the welding area with water coolant during welding, is to minimize the loss of strength in the heat affected zone. So a heat treated alloy like 6061 T6 retains much of its strength in the weld area and in the heat affected zone. The second part of it is most of the outer surfaces of a mass seam weld consist of wrought material microstructure. The outer surfaces are not melted together, are not melted during this welding because they are in contact with water-cooled copper alloy welding wheels. And since they are not melted, they retain the wrought microstructure and the corrosion resistance of the wrought metal itself. So these two are very attractive for boat manufacturers. There are a good number of aluminum boat manufacturers in the Detroit area and also aluminum shipbuilders in the United States for the US Navy. I'm working to, and also automotive body panel builders in the Detroit area. I'm trying to do the mass seam welding for these applications. The second part of this application is to enable mass seam welding of aluminum for very thick and thin combinations. And for this reason, I have an ultra high current seam weld machine, which can go up to about 125,000 amperes. And these are for welding some posts and other aluminum structures onto an aluminum base in a ship or a boat. I'm mainly developing these for boat, ship, and some automotive body panel welding. Thank you so much for the lecture. I don't know whether you care experience on microwave welding of aluminum alloys. Sorry, I have not done any of that. I have not done any microwave welding on aluminum alloys. We have done magnetic pulse welding, AA52 tube to stainless steel 304 plug. What are the different weld specifications? With a magnetic pulse welding, I believe you are doing something circular or tubular, probably. You're somehow making something collapse onto the other part and do a good solid state weld. What kind of qualification I would do? I would do some peel testing to see if the joints peel off or if the weld is stronger than the parent metal weld, weaker of the parent metal welded. And then I would do some cross sections to see how the welding process has progressed at the weld interface and whether it has pushed out all the dirt and all the asperities in the weld interface effectively out of the intended weld joint. So I would do some, if it was for some cyclic loading service, I would subject it to some cyclic loading tests as well. But since you're welding an aluminum alloy tube, I would think that it is probably not for a cyclic mechanical loading application. You're probably looking to get just good metallurgical bonding, in which case I would do a peel test to see that the weld is stronger than your aluminum and good metallographic examination. If we weld type 304 stainless steel pipe or standard schedule 316 SS after welding. Okay, I answered this question already. How to write to Dr. Anthony? You have my, hold a second, I'll go to the last. You have my email address at the bottom of the slide, and you can also get it from Dr. Krishnan, and I'll be happy to entertain questions from this group.
Yeah, I have already given your mail ID.
I say, okay, thank you. Which process, GTAW or GMAW, advisable to weld thin sheet lap joints? Example, on the roof of a train car or a sidewall. Yeah, you can, if your volumes are large, I would recommend using GMAW with very good welding current pulses, as I showed in some of my earlier slides. Particularly because I believe that these are not subject to too much loading. They're mainly meant for providing a good cover. I'm not sure they are subjected to a lot of mechanical loading. So a good GMAW with good productivity may be a good answer for you. If you need very good leak tightness, very good strength and very good functionality, like a gasoline tanker welder, then you probably would do very careful manual TIG welding as they do. Is preheat mandatory? Yeah, in fact, I would not preheat these metals at all for welding. Because preheating, if anything, only oxidizes them and makes the weld bead wetting and the weld bead starts more difficult. So I would not at all recommend preheating for these alloys.
Yeah, I think you have addressed all the questions.
Yeah, thank you. I have answered all the questions. If there are any more, I'll be happy to take them.
We can write, and thank you so much. Now I invite Dr. Ashok Malge. Ashok Malge, please give vote of thanks.
Yeah. Am I audible?
Yeah, very audible, yes.
Yeah. Good evening, everyone from Mumbai. This is Ashok Malge, Secretary, Institute of Welding, Mumbai branch. Today's WeldTech talk on practical challenges in the welding and of aluminum alloys was very interesting, and it's practical oriented. Dr. Ananthnarayanan covered basics of basics and weldability issues, sensitization, corrosion, hot cracking, loss of strength, dilution, and many more technical points. And he also could answer a lot of queries from the audience. Also, the latest item of use of aluminum and EV vehicles and cable welding, etc., was also covered. Is quite interesting. So many times he also mentioned that he is volunteering to work with interested groups, which is a remarkable contribution from his end, volunteering himself to help us in India. So I thank Dr. Ananthnarayanan on behalf of Institute of Welding Mumbai branch for giving an excellent webinar today, which has helped all the participants to gain some knowledge and use that in practical way. I also thank all the participants who participated in this webinar across the globe, and also our technical team in organizing this WeldTech talk. It was a good and learning exercise for all of us, because aluminum itself is a tricky material to be welded. So a lot of practical issues were addressed, and I thank profusely Dr. Ananthnarayanan for this particular webinar. Thank you, sir.
Thank you so much. Thank you, Doctor.
Thank you, Dr. Krishnan, and everybody at the IIW Mumbai branch for arranging this talk. And thanks particularly to the entire audience who have taken the time on a Saturday evening away from their families to listen to a guy talk some technical stuff. Thank you for your time. I look forward to working with any of you if there is an interest.
Yeah.
And wish you all the best.
Thank you. Thank you so much.
Thank you very much, sir. We sign off.
Thank you.
Thank you very much.